So you already saw there are only 2 slides because this is a live demo using our g.BSanalyze MATLAB-based software. So let's just start our software. It started from our GTEx read, as you may have already seen. You go to the MATLAB tab, and there you have the MATLAB-based programs. The g.BSanalyze, the HYSYS is the Simulink based environment, and then we have the montage creator that I will also show a little bit in the demo. I click here on open to open g.BSanalyze. You can also go to the manual. I already opened it here. So it takes a little bit until there we have MATLAB and g.BSanalyze. That's the main window. You may have already seen it yesterday when Download Iremia was showing some things in g.BSanalyze. So I would like to start with an easy demo where I use this data that you can find also in the standard installation of g.BSanalyze. And the analysis I would like to show you is described in the IFU. So if you have the software, it's easy for you to reproduce all these single steps that you would see. I go in the instructions for use to the chapter 12.2 average. There are 3 examples. I will not show all of them to you here. Let's just start with example 2. That one here. Example 2. We have a data set called EP8 channels.mat. You find it, as I said, when you have installed the g.BSanalyze software. You find in the user manual the location where the test data is stored. Documents, GTEC, g.BSanalyze, test data, evoked potentials. So let's just go there. Sorry. So here's the data editor. I go to load data, documents, GTEC, g.BSanalyze, test data, EP for evoked potentials. Where is it? Here. Oops. And the 8-channel data. All right, here we are. Main window of g.BSanalyze. You see the loaded EEG data. You see here on the y-axis the channels. We have 8 channels in that example. Channel 1 to channel 8 already having the correct name according to the extended 1020 system, international system, FZ, CZ, and so on until P008. And on the x-axis, we have the timeline here in seconds. So we have 0.1 second until 0.7 second, which is 1 trial. This means that data is already triggered. So it means single segments of data is already cutted. And of course, these segments contain the event-related potentials. So let's zoom out a little bit. A change here on the bottom, the display time from 0.7 seconds to maybe 7 seconds or 8 seconds. Now we should have 10 trials because what we have, or a little bit more, that's important. Yeah, we have a number of trials. You see here these green lines and the black lines. Let me try. I need to move this bar from Zoom, sorry. It's overlaying my Here we are. Just overlaying my screen. You see here on the bottom, you can enable or disable certain visualizations. For example, the green lines are the trial attributes. It takes a while until they are plotted new. Those are the channel attributes. Okay, maybe we don't wait that long. They would disappear and appear again. We can scroll through the single trials. We see here some bit artifacted, like here on the last channel, we have this bit behavior. Maybe should be marked as an artifact, but we will come to that later. Also here, that one seems not nice. But anyway, let's continue. What we would like to do with that data is to plot the average of evoked potentials. So we have target and non-target trials of a visual evoked potential paradigm. So I go here in the menu to analyze, and there's the function called average, and it opens up. And you see we have here a lot of options to select. Let's start at the top. We can do a baseline correction. That's always recommended. Baseline correction means that you remove any DC components. If there are DC components on the data, means they're not on the 0 line, they're maybe shifted up or down a little bit. And when you average over a number of trials and they are not around the 0 line, then of course this would influence highly the average. So it's always good to remove the baseline. So we do this baseline correction. And in the data, we have already defined a reference interval. You see here, the black line is the start of each trial, and the green line is the trigger event when the visual evoked stimulus or visual stimulus appeared. So the 100 milliseconds between black line and green line is our baseline because it's before the stimulus appeared. So we take this for the baseline correction. And we have to define here the reference interval. It starts at 1 sample and until 100 milliseconds. You see here always these two boxes, milliseconds and samples. So depending on the sample rate, if you enter or if you edit one of the boxes, the other box is calculated correctly. So yeah, for example, 100 milliseconds would mean 26 samples. I think that's a sample rate of 256 Hertz. If we would enter here 50 samples, then the milliseconds would change immediately. Let's go back to 100. So we have two classes, target and the non-target trials. So we would like to compute here separate averages for different classes. And then this window here is activated. These are the 4 classes that are defined in our data: artifact, remove, target, and non-target. The artifact and the remove would be markers that we could use to mark artifacted trials or to mark trials that we would like to remove, which we didn't do yet here. So these 2 markers are already defined, but they're not filled with any trials. But the target and the non-target trials are already defined in the data. And these are the ones we're interested in. So I mark those 2. So we have the option, these compute separate averages, and for target and non-target. And additionally, I can say, I would like to use a statistical analysis. That's what I can do when I have more than one class. If I would have only one class, I couldn't do it because the statistical analysis calculates the statistically significant differences between samples of classes in the trial. I could do a smoothing, a downsampling to save some calculation time, but it's not relevant here. My computer is quick enough. And everything else is also set nicely. So here we have show with result 2D. This means we will receive a result, a visual plot. No need now for saving it. So I just click on start. And it's calculating and plotting. And there we are. We see those 8 channels. So one plot for each channel and 2 lines in each plot, which means green line, that's maybe a little bit too small for you to read, I'm not sure, but here's the legend. Green means target trials, average target trials. Blue means the averaged non-target trials. And these areas here and here are the significant different areas between the 2 classes. The dark areas is highly significant, meaning p-value lower than 0.01. And the light areas mean still significant, p-value smaller than 0.05. If you're interested in a certain plot, you could, or maybe you're interested in, sorry, don't know if I can disable the taskbar so I see. No, it's better. Nope. Let's try this. Okay. The problem with my small screen on the laptop, I'm not used to that. Maybe you want to change the scale of the plots. You can click on scales and you can change the X scaling and Y scaling. Maybe now we're not interested anymore in the baseline, the 100 milliseconds before the trigger. So we could change the X scaling to 0, and maybe we don't need the full 0.6 seconds here, maybe until 0.4. So we could do this and click on OK. And now have it plotted again. Maybe you're only interested in one plot. Let's say the second one. You could go here on the bottom to select. And you see here, okay, you can select second channel. Click on OK. And did something wrong, sorry. Let's try it again. Didn't mark this, I guess. So don't forget the checkbox. Yeah, here we are. And you see now the channel number 2 in big. All right. Next thing I would like to show you is analysis of MindBeagle data, of our new MindBeagle that Ren showed you today. So in g.BSanalyze, we have an importer function for different kinds of data sets. We can import RecoverX data, CortiQ data. Here's the RecoverX, here's the CortiQ, here's the MindBeagle. And you may recognize some of these data formats, EDF, PDF, ASCII is clear. Yeah, let's go back to MindBeagle. Let me quickly change the folder to where I've stored the data. It's a bit easier for me. Okay. Again, I go to import, MindBeagle, and select the data. While it's loading, I could show you. That's the MindBeagle data I'm just importing. It was an AEP assessment. I, for myself, was the subject, reached 86% of accuracy. And you see here one of the ERPs on CSET. If I would scroll down, you see here all ERPs. You can rotate clockwise, then you see it a little bit better. That's the montage, the geometry, as we have the 16 channels that we are using, and ERPs of all 16 channels. Now, in the meanwhile, data has loaded. You see it here in g.BSanalyze. Looks on the first glance weird because here it's empty and you see only one line. That's because data is stored completely unfiltered in MindBeagle and also in Recurvex, because then you don't lose any information and you can do the filtering anyway later on offline, and I will show you how to do it. And then we will see EEG as we are used to it. I'm just scrolling down. We have here 16 EEG channels, as you already saw this montage, plus 2 additional channels. One is the trigger channel. Let's just scroll down to the right and change the scaling a little bit. To go here to auto scale. Okay, that's better. Now we see here on the trigger channel this rectangular events. These are hardware triggers. Created, it was an auditory paradigm, so the sound card created the stimuli in parallel to the auditory beeps sent to the patient. Stimuli were sent back to the PA signal amplifiers. And this is what you see here in this, with this rectangular impulses. And this allows us to absolutely precisely track the time points of stimulus onsets, because sometimes if we just track in the software the timing, then we could have some jitter, some discrepancy between the time point Windows is writing to the time point when Windows is really sending the auditory stimulus, because Microsoft Windows and other similar operating systems are not in real time. They're not designed for that. So how Windows controls the hardware is not 100% in real time, and there can be a small delay that can be different for each stimulus, and that's what we call jitter. And if we would just write down the time points, then sometimes we would have imprecise data. So that's why we also record these hardware triggers. You see here also in the vertical lines the software triggers. And in this case, let's zoom in a little bit again. Software triggers and hardware triggers are very good matched. So no need in that case to use the hardware triggers. But I will show you still both options. First, how to use the software triggers, and then how you would use the hardware triggers to do an analysis. The last channel is the validity channel. This one is either 1 if data was valid, or 0 if there was a problem in the wireless data transmission between our wireless headset, the g.Nautilus, and the base station. So as you can see, it's always 1 here. Data was always good, but it's still good to have a check to have this information recorded. I just recently saw a case where someone placed the Nautilus headset just behind the computer screen, so screen was in between headset and base station, and then of course the wireless data transmission was interrupted, and then the data that you get in the interrupted events is of course not valid, and you would have to take care for that. But yeah, all good here. So let's continue. As I said, data is not filtered yet, so let's do that first. Filtering, let me see. Yes, for filtering, we go to Preprocessing in the menu, and then filter. There's a number of already predefined filters in g.BSanalyze, as you can see. There's a name, the type of filter, bandpass, then in this case, the lower cutoff frequency and the higher cutoff frequency. The implementation, FFT filter or Butterworth filter or whatever. And the filter order. So filter order 0 for FFT filters. These would have filter order 5. You can also design your own filter if in this list there's not yet a filter that you like. You could design your own filter and then store it and add it to the list. And the next time you just go to the drop-down list and select your filter. So in the design filter, you can choose the filter type, low pass, high pass, band pass, or band stop. What we would like to have here is a band pass filter between 0.5 and 30 Hertz. I usually use a Butterworth filter. We see here already 0.5 Hertz lower cutoff frequency. We have to change that to 30. You see here is a plot of the filter, how it will behave. So you see here the cutoff frequencies and the suppression. We can increase the filter order to 4 or 5. Then we can give it a name. Spring School 24. And add it to the list. You see I already created a Spring School filter. This is the new one. All good. I click on OK. It's selected here. And important not to forget here is to not filter the last 2 channels, the trigger channel and the validity channel, because these are these rectangular signals. They don't need a filter. You would have destroyed a little bit your signals if you would filter them. So I click here on select trials and channels and can say which channels should be filtered and which one not. Here I can specify the channel number and can say exclude or include. It's easier now to exclude channel 17 and 18 from the filtering. So 1 to 16 are my EEG channels that will be filtered. The others not. Click on OK, and now everything is set, and I click on Start. Okay, picture already changed. You see here this transient. This is because of the filtering. When you start acquisition, you have a jump from 0 to any any value, and when you filter that, you will have always such transient until the filter goes back to the 0 line. And our data, the scaling of each channel is automatic, so it takes the max and the min, and the max, because of this initial transient, is very high. And this is why it looks like this. It looks flat because we're not zooming in yet. So we will have to change the scaling to see the nice EEG. Before that, let's go back to the filtering, because what I forgot is to apply a notch filter. We always have the 50 Hertz or 60 Hertz, depending on where you are. In Europe, we have 50 Hertz power line interference. In the United States, Mexico, I think Canada, some other countries, you would have 60 Hertz. So if you go back to this filter dialog, you have here the option to filter the power line frequency. You can choose 50 or 60 Hertz. As I said, data here was recorded in Austria, so we have the 50 Hertz. And I click here on the cascaded notch filter and click on start, and apply also the 50 Hertz filter. And I just see I did a mistake, because now I also filtered the last two channels, and you see it is weird ripples now. But that's not a problem if you do a mistake. g.BSanalyze has an undo function. So click here on undo. And so now we are one step back. Let's do it correctly. I go back to preprocessing, filter, cascaded notch, and again, exclude the last two channels. And now I'm ready to go. Start. All good. Now let's change the scaling and see our EEG, if it's real nice EEG. So I go to View, here the third option, and Scaling. And I see these 18 channels. And I only want to scale or rescale the 16 EEG channels. So what I can do is to apply a new scale. 50 microvolts is always a good value, or maybe 100 microvolts, whatever you prefer. And I want to apply this on the channel 1 until 16. And I click on apply. And now I see it's changed. Just change that back to 1 microvolt and that 2. Okay. And yes, now it looks good. Nice EEG. As I said, you have here in the beginning these transients, big waves, but then you have the EEG. And you see it's not a problem to have those transients, because I have to scroll a little bit to the right until second 26 in that case to have the first stimulus event, which means data at the beginning is anyway discarded, cut it away. The filters are already good at the time point where our stimulus begins, stimulus sequence. Right, so let's see. We have those EEG events. We have here the hardware triggers, and the vertical lines are the software triggers. Let's continue. I would like to do one extra step and load now the geometry. Geometry is the three-dimensional geometry setting of the positioning of the EEG electrodes. And if you provide g.BSanalyze that information, you can have this topographic plot, as you have seen here, where it knows the positions here in 2 dimensions, the positions of each channel in the view from the top. And that way it's you have the better overview of your data. Before I load this geometry, I will remove those 2 channels that we don't need anyway, because we will use the software triggers. And these channels don't have a geometric positioning, so we have to remove them. So I go to transform, cut trials and channels, and then I select what I would like to cut. I can cut trials and I can cut channels. So what I would like to do is to cut the channel number 17 and 18. Select them, click on OK. It shows me here the overview. Okay, I have currently 18 channels. 2 will be cutted, 16 will remain. All good. I click on Start, and they're gone. For the geometry, I have to go here to header geometry, so the second from the left, and then down to geometry. So you see here the current geometry. We have the correct names of the channels, but the positioning in the 3-dimensional space would be the coordinates are all 0 for each channel, so it does not know the 3-dimensional setting. That's what we would like to load. You can go to the Gmon creator to create such a geometry, or maybe you have already created one and can load it. So of course I already did that. I can go to File, Load Montage, and click here on EEG. That's the one. Here we are. I make it full screen. Again, I'm not sure how good this is visible via Zoom for you, but you see channels FC3, FCZ, FC4, and those here, those 5 and PZ is marked. So these are the channels that I have in my setup. If you would like to create your own setup, and maybe you have acquired also POZ, then you would click on the channel you would like to add to your file and just click on confirm. Then now I would have 17 channels in my setting. Can click on clear again to delete this. You can have a quick look in the 3-dimensional space to your montage. I clicked here on the show with gResult 3D. Takes a while to open. Yes, here we are. And you see here, that's the EEG setting, how we used it. Our 16 channels, you can view from the side, but it's all good. You could change here the view, but it's now not so important. Let's just continue. I close it. And I can also close this one because the file is stored. And I go back here to just load my stored file, browse. Again, it takes a while. There we are. Was the file called EEG. And now you see this has updated. You have now the real positions in X, Y, and Z coordinates loaded to the file. And so we can close it and we can continue. Now it's time to trigger. What we currently have is the trigger information in the data. But now we have to tell the program to cut out the segments, the trials, how we call it, so that we can later do the averaging or other analysis. So to do that, I go to transform. From here it is. Fourth menu point from the left and trigger. So what we have here, we can say define on what kind of trigger we would like to trigger. We could use physical channels, that would be the hardware trigger, or we could have markers. These are these software triggers, these vertical lines, and we said we would use them. You see here in the menu all kinds of markers as they were loaded into the software, defined by the Mindbuilding software in that case. So we have different kinds of non-targets, different kinds of targets. But what we would need is the class called target and non-target. So this non-target summarizes all the sub non-target classes, and the target also summarizes all target subclasses. Before I continue, I forgot to specify here in the time before trigger and time after trigger how long my trials should be, the size of the trials. So again, it's good to have a baseline before the trigger to do this baseline correction. So we define again, sorry, not 100 samples, we define 100 milliseconds baseline interval before the trigger. And I usually use 700 milliseconds after the trigger. Now let's go back. I define my first marker, the target trigger. Then I can give it a name here. I call it target, makes sense. And then I click, when everything is defined, I click on add to list. I have here a list of as many triggers I would like to define in the step. So I will define 2 triggers in this case, but you can define as many as you like. The second one I define is the non-target. So go again to the marker, select non-target, give it another name, the non-target, and click again to the list. Now I have 2 different triggers defined, and everything else should be good. We take all channels, nothing to select here, and just click and start. And let's change the scaling again. So what we see here is now the segments of data, the trials. You see here trial 1, trial 2, trial 10. If I go to the very right, I see that I have 270 trials. And now I activated again the trial attribute. I see these are all non-target trials. And at the beginning I'm a target trial, so they're not anymore ordered by time. I just have at the beginning all target trials and then all non-target trials in g.BSanalyze. All right, let's continue. We have now triggered, so now we can do again this averaging. I go to analyze and average. And again, I would like to do a baseline correction because we just have defined it. Correct for the reference interval. We use the 100 milliseconds reference interval. Again, we would like to do separate averages for different classes, target and non-target, and the statistical analysis. And again, I don't need to change anything here. So click on Start. And it's plotting, yes, my 16 channels. I see nice differences between target and non-target, also significant differences in all channels. What's a little bit weird is, for example, here, the third channel, you see this gap here, long-lasting gap between green and blue line. So it appears that the data was not clear on all trials. So we have maybe some drift on some trials that ruined the averaging. So what we could do is to try to find those trials and correct the problem and try to do the plotting again. You will never or almost never have 100% clear data. There are these nice new tools like the Oscar that was already shown by Martin and Johannes. Unfortunately, I don't have that yet in that version of g.BSanalyze. So I have to use other methods to account for it. So the two possibilities I have is to do a kind of a calculation, automatic correction of the problem, or go through trials visually and mark them and cut away the artifact trials. I would start with the automatic method because it's the quicker one. Let me see where do I find it. The menu is so big that it's sometimes, yes, hard to find. So I would like to do a D-trend because, as I said, it seems there's a trending in some trials, and I could try to improve data by just applying a D-trend over all trials. So you find it here in Preprocessing D-trend. And I would like to correct for the individual trend, trial by trial, and entire trial. And this means I don't need to do any more settings and just click on Start. And it's applied. Takes a while. Yes, now it's done. And we could immediately see or try if we have a good effect. So I go again to Analyze, Average, do the same plotting and see if it looks better now. We do again that baseline correction. Separate averages. Target, non-target, statistical analysis, and click on Start. And I see, in comparison, I still have the other window open. So this was the old one that we plotted first, where you see this gap, especially here, but also here. And I switch to the new one and see that the detrending already worked. So this looks now much better. This also, let's flip. Well, it decreased also a little bit the gap here. But yeah, in total, I would say result is already a little bit better. But what we could also do, as I said, is to do this manual, this visual search for artifacts. Click here, cancel, close the window. We could do the undo button to undo the detrending and then have a quick look into the data and look for artifacts. To do that, I change the scaling to 8 seconds to have more trials here. Now I can select a marker. Usually I select the marker called artifact, but it could be any marker. You can call it, of course, however you like, and apply that marker on the artifacted trials. So how does it work? I selected here the marker. And now if I click on the data in one trial, the marker is applied. So now space for writing is a little bit too small. I zoom in again. Here you see it, the trial 2 would have now these 2 markers. It's still a target trial, but it's also marked as artifact. I click again and this marker is gone. So you toggle it by clicking twice. So let's go quickly through the trials and see where there are artifacts. So this, for example, has here negative drift. I could mark as an artifact. Just have the zoom bar again in my view. This one looks not good. This positive drift here, I mark it as artifact. Also that one. Here's a drift. This doesn't look very good. It's already marked. Good, and maybe that one. Here's a big drift. Let's remove it. Okay, we are now already in the non-target trials. They're not so important, so let's be a little bit quicker. Also, time is running low. Here's one. That one. Big. Two. Okay. I think you get the idea. I don't need to show you now all data and all artifacts. You just go through it and click on the ones you want to remove. Let's see if this already has an effect. I go again to analyze and average and try to plot it again. And select again the baseline, reference, 100 milliseconds, separate averages, target versus non-target, statistical analysis. And now I have to tell the program to discard the artifact marked trials. So go here to select trials or channels. You already know the window from before. You could select channels or trials. Before we have discarded the channels 17 and 18. Now we want to define trials. And it could again say include only or exclude. So I want to exclude all trials marked as artifact. There are 13 of them. Click on OK and click on Start. Did I click? Yeah. And you see again, the gap here is maybe not perfectly closed. Okay, now click twice on the start, so it's plotted twice. Anyway, because I was a little bit too sloppy in marking the artifact trials, I would have to invest some more minutes maybe, but it's already much better than in the first trial again, which was this one. If I jump between them, you see, I would trust that data set already much more than the other one. You see, by the way, here on the right side, the information that we have now 38 target trials and 290 non-target trials. I jump back to the first one, where we didn't cut away any trials, and we had 45 target trials and 225 non-target trials. Okay, I think that's a nice ending of the presentation. Maybe there's some questions. If not, I thank you for your interest. I hope it was interesting.
Somebody's asking, is memory or CPU speed the biggest factor for improving the calculation speed during the analysis?
Depends on depends on what you're doing. Currently, if you don't have too many channels or not too high sample rate, then the memory is not a big problem. If you would go for ECOG, you have higher sample rates or higher number of channels, then you need a big memory. But in this case, in my calculations, the CPU speed is the limiting, or more the limiting factor.
For big data sets, of course, it's also important that you get a fast hard disk, otherwise it's taking forever to read it in. So a good trick is to keep data size small, and then the processing goes much faster. So Rupi, thank you very much for the step-by-step introduction for the
My pleasure.
analysis. It was very nice.